So if you haven't noticed, but we are a little bit behind, we should be able to make up time. 5.4 is short. We might have to decrease the number of examples we look at in 5.5, but I won't skip stuff so that, well, let me rephrase that. The things that we skip, I hope that if we do have to skip things, that we still get the main idea of the sections we have to cover. So, are there any homework questions? Yeah.
I just had a question on, it was 5.3, number 13, just the very last part. It was just asking for the net area.
Okay.
And then the area. And when you take like the integral of the original function.
This one.
Yeah.
Okay. So area versus net area?
Yeah. And it ended up being exactly the same, but it was on a parabola.
Oh,
so I didn't understand when it's going to infinity, how you're supposed to find that.
So the area here versus the net area?
It gave them both the exact same.
Yeah, they are the exact same. Here the net area is the area because everything is above the x-axis.
Okay.
So if we have something, let me show you. So I think it's important to address the differences. So if we look at a function like this, the net area is the contributions of this positive area and this negative area. So that's A minus, well, I'll call it A1 and A2 because they're clearly different. That's the net area. If we take, instead, let's look at it this way, A1 plus the absolute value of A2, that gives us the area. In other words, any negative areas that you have indicating areas below the x-axis, you just want to knock off the negative sign and add that to the areas above the x-axis. Does that make sense?
Yeah, so I guess okay, yeah, I guess that makes sense.
So like, if what was bounded in blue was the land you owned and like the x-axis is a river, you want to think about area as how much land I actually have, right? The net area would be how much land is north and how much land is south.
Okay.
Kind of, I don't know if that's a good analogy, but that's, it does, the concept between net area and area does show up again if you're moving on. So a practical way to look at that is that the net area, we don't see this, but the net area is given by the integral from a to b of f of x dx. And I guess one physical application or context to this is the displacement. When we think of f of x equal to a velocity function, maybe. So the net area on the velocity function gives us displacement, whereas area, I don't like the way that's written. I'm gonna write this. But we can substitute whatever we want in here. Okay, so that's a for the net area, we could view it in certain instances as a displacement, whereas the area, we would look at the absolute value. Because and all that's doing is ensuring anything that's negative is now positive, and then this would be the distance traveled. Right, so you don't really have to take away anything from this. I'm just so again, if we have something like that, the displacement, I view that as like me walking back to this wall and back to where I started. The change in position is 0 because the net area is 0, but the distance traveled is actually twice what I walked, right? So that's 2 times this right here. In other words, when we look at, this is the integral, let's just say of some function. That's the definite integral, oops, for net area compared to the, if we looked at the function this way, that would be the integral of the absolute value. So whatever's negative, we make positive. Okay, so that's the total distance traveled. Above is the displacement or the change in position. I guess, I don't know, there's a few ways to think about that, so hopefully that's helpful. Okay. Any other questions? Okay, let's pick back up then in 5.3. We were talking about how to evaluate these definite integrals in a much more efficient way with the fundamental theorem of calculus. So it says in order to evaluate these kinds of things, we first have to find the antiderivative of the function in front of the integral, which is called the integrand. And then we evaluate the antiderivative at the upper limit, subtracted the antiderivative evaluated at the lower limit. So in example 4, we saw an example similar to this on the test where we just said find the antiderivative of this function. You've got to remember, like, products and quotients, there isn't a rule to find the antiderivative for those. You see that in Calc 2. So when you see products and quotients, you want to think simplify that first before I take the antiderivative. So we want to simplify this first. That means we're just going to divide square root of x by x and negative 1 by x to separate that out. So what's the square root of x divided by x?
1 over the square root of x.
1 over the square root of x, or x to the negative 1/2. And then minus the 1 over x. So we have to simplify that first. The first term now, we use the power rule for antiderivatives. And the second one is going to be what? What's the antiderivative of 1 over x? Yeah, natural log, absolute value of x, yeah. So power rule, we add 1 to the exponent and then divide by the result. So a negative 1/2 plus 1 is positive 1/2. And then we're going to divide by 1/2, which means multiply by 2. Antiderivative of 1 over x is ln of the absolute value of x. Okay. So this is our antiderivative. We're going to evaluate that from 1 to 4. So you always want to make sure that when you take the antiderivative of 1 over x, that you're saying it's the natural log of the absolute value. Then, depending on where you're at or what you're doing with that, you can determine, is the absolute value necessary, or can I just drop it? Here, since we're in a positive region, we don't have to worry about taking the ln of negative numbers. So the absolute value in this instance isn't necessary. Okay, so this, just so we're referencing back, this is capital F of x. So that's our antiderivative. Then we evaluate it at 4. So we have 2 times 4 to the 1/2 minus the natural log of 4. We subtract off the antiderivative evaluated at the lower, so minus. And since we have more than one term, you want to be careful because we have to subtract off that entire quantity. So we have minus the quantity 2 times 1 to the 1/2 minus the natural log of 1. Are there any questions on where we're at? All right, so let's go over here. We have 2 times the square root of 4, so 2 times 2 is 4, minus ln 4. And we have minus the quantity 2 minus ln 1. ln 1 is 0, so we have minus 2 there. So that 4 minus 2 minus ln 4 is the exact area, or the exact net area. Questions on that? So this is much more easy of a process than actually computing the sums and then taking the limit as n goes to infinity. But it's still a pretty tedious process. The thing with derivatives is we had set rules to find a derivative. No matter what kind of function we dealt with, it was, oh, hey, use the quotient rule or the chain rule. With antiderivatives or integrals, it's not as straightforward. The advantage of these things is once we find the antiderivative, we can always check, did I take the antiderivative correctly? Because the derivative of capital F should give me back my original function in front of the integral. So that's sort of the trade-off. They're harder to deal with, but they're easier to check that you actually did it right. With derivatives, you just had to hope you applied the rules correctly. Okay, how about example 5? The primary thing here is being able to find the antiderivative of these functions. So what's the antiderivative of 1 over the square root of 1 minus x squared?
Sine inverse x.
Okay, good, yeah. This is inverse sine. There's really, even once we get to our technique of integration, which is a substitution technique, if you don't recognize that as inverse sine, in this class anyways, there's really nothing you can do. If you don't recognize that as inverse sine, you're just stuck. Like I said, inverse sine and inverse tangent are really important antiderivatives. Okay, so the antiderivative inverse sine of x evaluated from 0 to 1/2 gives us inverse sine of 1/2 minus inverse sine of 0. What's the inverse sine of 1/2? In other words, the sine of what angle gives me 1/2?
Pi over 6.
Pi over 6. And the inverse sine of 0?
0.
0. With pi over 6 minus 0, which is pi over 6.
So my math lab takes the answer of sine inverse 1/2 minus sine inverse 0. Would you want us to simplify in the exam?
Yeah.
No.
Yeah. So please, you got to stay up on these antiderivatives. It's just as crucial on the final as it was in chapter 4. Any questions on what we're doing? Okay. Example 6. That's the antiderivative of cosine 2x. Sine 2x over 2. Evaluated from 0 to pi over 4. I forget which one this is in your table, but it's the integral of cosine of ax dx equals to 1 over a sine of ax. So we could deal with the 2 in both of our terms, or just, we could take it out, because it's 1/2 times of that function of x. And remember, these bounds here are just for things involving an x. So you don't have to do this, but I usually do. You can take that constant of 1/2 out, and then just evaluate sine 2x from 0 to pi over 4. And then multiply your result by 1/2. Okay, so we have 1/2 times, what's the sine of 2 times pi over 4? I'll try to fit that here, sine 2 times. Sine of pi over 2 is 1. So that's 1/2 times the quantity 1 minus the sine of 2 times 0 minus the sine of 0. 0. There's just 1/2 times 1. If you left the 2 in from where we were originally, then you would just have, 1/2 minus 0 over 2. Same thing. Any questions on that? Okay. How about the function 7, integral of 10 e to the 2x? It's the antiderivative of that.
1 over 10 e to the 2x.
Okay, so let's see what others think. 1 over 10 e to the 2x.
Yeah.
What do y'all think? Antiderivative of 10 times e to the 2x.
Where they just be
10. No, 28. I don't know.
So integrating with respect to x, that 10 is just a constant times the function of x. So maybe think of it this way. It's 10 times the integral from 0 to 1 on e to the 2x dx. Does that help?
That would just
5 e to
Right.
2x then.
Yeah, that makes sense.
So let me do this here. So this is in the table as well for finding the antiderivative of e to the ax. We have e to the ax over a. So the antiderivative of e to the 2x is e to the 2x over 2. And again, evaluating that from 0 to 1. We'll take care of these constants. So we have 5 times e to the 2x evaluated from 0 to 1. And so that's going to be 5 e to the power of 2 times 1 minus e to the power of 2 times 0. So I hope at this point the fundamental theorem of calculus seems pretty standard to work with. You just might have to revisit antiderivatives. But at least I hope that first part we can do. So we have 5 times e squared, and e to the 0 is 1, so 5 times e squared minus 1, or 5e squared minus 5. Are there any questions? So the last portion of this, what's wrong with the following calculation? Give you a second to think about that. So we are thinking about this, hopefully this way.
When you have the x squared, can you use ln?
The ln would be for just 1 over x.
Okay.
Is it where it says it equals -1 over x? Because technically doesn't it equal negative x over -1?
Yeah, so this is equal to negative x to the negative 1. And if, yeah, we could evaluate from here, but notice, oops, sorry, negative 1 to 3. Negative 1 to x to the negative 1 is the same thing as negative 1 over x to the positive 1, which is what they have here. Because that's that's what we're looking at there. So it doesn't seem to be anything wrong with the antiderivative up to this point. Is there anything wrong with how they've evaluated this? I plug 3 into this, so I get -1/3. And then I have to subtract off the same function evaluated at -1. We have -1/3 plus 1. Or sorry, -1. -1/3 minus 1 is what they have. Doesn't seem to be anything wrong with that. And then that -1 is -4/3.
Aren't you evaluating the wrong thing?
What thing?
You're evaluating one of the totals instead of, like, you just want to put
No.
Okay, just kidding.
I need to elaborate.
Just that the function is.
Because when you do f of b minus f of a, aren't you supposed to be using the negative x, the -1 for both? Not
Yeah.
the -1/x? So you're evaluating wrong.
Well, the -x to the -1, if you want to see it in a different way,
Does it give you the same answer?
yeah. If we use -x to the -1 from -1 to 3, we would have -3 to the -1 minus -1 to the -1,
Oh,
right?
Yeah.
Because that minus is already, that minus regardless is in the fundamental theorem right there. So let's just look at the original function. What we're seeing is that maybe, like, I'm not convinced that there's an error in this computation. What I'm looking at is says find the net area on the function 1/x² from -1 to 3, right? That's what that symbol means. So I don't know if that's helpful. If not, we can certainly look at the function. And if I go from -1 to 3, what's wrong with our computation?
It's not hit the x-axis.
With what?
It doesn't touch the x-axis, is that one?
Yeah, what happens at the x-axis on the function 1/x²?
It doesn't hit it.
It doesn't hit it because there's a vertical asymptote.
You mean horizontal?
Vertical. Because we're only going from here to here. So that horizontal asymptote isn't in effect. I can draw on this. I don't know if it's a word, but
Oh, I see.
no. Well, let's change this. So we're stopping right there, and we're stopping right there. So we're saying what's that net area? What's all this area and all of this area? So the problem is not with the computation. The problem is with the function over the region specified. So f of x equals 1/x² is not continuous on the interval -1 to 3. That's what's wrong with the computation. You're trying to find the net area over a vertical asymptote. You'll see this if you move on to Calc 2. Sometimes these do have finite areas. Even though we're integrating up to like an infinite thing, there can still be a finite area. It's just another one of the paradoxes that arise when dealing with limits. But this is not the way to compute that. Anytime you're integrating over a discontinuity like an asymptote, you have to involve limits. And that's all I'll say about that. But that's why, if we revisit the fundamental theorem of calculus, it says that this statement is true if f is continuous on the closed interval from a to b. Now, it's not something in this class that we normally have to even check for or to pay attention. I'm not going to throw a curveball like that at you on the exam either, but it is certainly a technical detail that's worth pointing out. Okay. In the last page here, I just wanted to mention the connection between the first part of the fundamental theorem and the second part. So the first part gave us that the derivative of the area function with respect to t was the function with respect to x, which says that if f is integrated and then differentiated, we arrive back at the original function. Okay, so derivative, antiderivative, inverse operations of one another. But since we're using the notation capital F prime for the antiderivative of f, or sorry, capital F is the antiderivative of f. Let's just make that note. It's really the same kind of thing from 4.9. So since capital F is the antiderivative of f, then capital F prime is f of x. So part 2 of the fundamental theorem can be written, instead of the lowercase f of x here, we can put in capital F prime of x, because that's the same thing, is equal to capital F of b minus capital F of a. So here again, we see that the derivative of capital F and the integral, or the antiderivative of capital F, gets undone in this step, but in a particular fashion. The one above, it just says it is the function. Here it says it is the function itself, but in a specific way. It's evaluated at b minus evaluated at a. So that version shows if we take the capital F, the antiderivative, first differentiated and integrated, the result will arrive back as the original function, but in the form f of b minus f of a. Again, solidifying the idea that antiderivatives and derivatives are inverses. So that's really kind of the whole point of that. So not only does it give us that fact, but it also allows us to evaluate these things very easily, because we know that the derivative of the area function is the function, which means the antiderivative of lowercase f is the area. And then I just took this quote from another textbook, but I mean, something so simple, it's really a very, very powerful thing. I do want to go back and look at both of those now that we have kind of both of those parts in context. If we revisit this problem and ask what is the derivative of the integral from 1 to x on the function t squared minus 1 dt. So according to the first part of the fundamental theorem, well, what should that be equal to?
T squared minus 1.
Okay, close.
X squared minus 1.
X squared minus 1, because we get the x that gets plugged into this f of t. By the fundamental theorem of calculus, part 1. We did some exercises like that last class. So let's look at this now in light of the fundamental theorem, part 2. So the fundamental theorem, part 2 says I'm going to evaluate that integral first. So in order to do that, I first find the antiderivative with respect to t. So what's the antiderivative of t squared minus 1 with respect to t?
So, 2 to the third over 3.
Right, it's t
Minus x.
cubed over 3 minus
X.
antiderivative with respect to t.
Oh, no, yeah, it's
T cubed over 3 minus t. And we're evaluating that from 1 to x. Remember, the variable of integration was t, so the bounds of integration are for t as well. So this is from a value of t equal 1 to a value of t equal to x. So now we're just going to plug in these upper and lower bound for t and t cubed over 3 minus t. So notice we haven't done anything with the derivative operation yet. So if I plug in my upper limit, I have x cubed over 3 minus x minus the antiderivative evaluated at 1 Is everybody all right with that? Okay, so now I can take the derivative of this stuff. The derivative with respect to x of x cubed over 3 gives me what? Derivative of x cubed over 3.
X squared.
X squared. The derivative of x, 1, minus the derivative of 1/3 minus 1. It's 0 because all of that's a constant. So we're done. X squared minus 1. That's the same result we had via the first part of the fundamental theorem. So there we see the derivative and the antiderivative just undo each other, and we just end up with that function t squared minus 1 as a function of x. Anyone have any questions on that? We talked about this last time, but just want to put it down definitively. The units for our derivative, as we've seen many times before, the units for y divided by the units for x. Because we're computing dy over dx. And the units for the definite integral were what? Does anybody remember?
X times y.
Yeah. Right. We see that here. This is y divided by x. But what we see with a definite integral is we see the y values times the x values. So the units here are the units of y times the units of x. So maybe think about this function f of x being a velocity function. Here on the y-axis or the velocity axis, we might have meters per second. And on the x-axis or the time axis, we might have seconds. So when we find the antiderivative of velocity, what does that give us?
The antiderivative of velocity is position.
This position. So when we multiply meters per second times seconds, we just get meters. That gives us a position. Same thing here. If this is a position function, seconds, and y is in meters, measuring the position, then the derivative of that, I divide my units, meters per second. Derivative of that gives me a velocity. So I guess that's one concrete way to look at it, but more generic way, derivative, divide units, antiderivative or definite integral, we multiply the units. Do y'all have any questions on this section? So 5.4, this is a pretty short section. We're just looking, we're kind of continuing with the theme of finding a definite integral. We're going to look at integrating with even and odd functions, and then we'll talk about the average value of a function. So these pictures hopefully shed some light on if I'm integrating around a symmetric interval from negative a to a, or from whatever, negative 10 to positive 10, negative 3.2 to positive 3.2, and I'm dealing with an even function, then what that's equivalent to is taking half of this area. So I can say, well, let me just look at half of this area. So I would look at the integral from 0 to a on that function to get this area. But to get the actual area that I'm required to get, all I have to do, since it's symmetric with the y-axis, is multiply that by 2. Does that make sense? So it's kind of what the theorem tells us below. Similarly, if it's an odd function, symmetric with respect to the origin, then if I go from a symmetric interval from negative a to a, the amount of area above the axis equals the amount of area below the axis, so that integral is just 0. And that's what we see in this theorem. The key here is that, well, there's really two things we're paying attention to. One is we've got a symmetric interval. About the y-axis, or x equals to 0. And then, depending on the function, if it's even, we can half the region and double it. So we half the region, find the area, and then we double that area. If it's odd, it's just the net area is 0. So I think we can see the efficiency of, if f is odd about a symmetric interval, that's just 0. Why is breaking the even integral up as 2 times the integral from 0 to a? What's the efficiency there?
Is it because of the 0? Just makes it easier to compute.
Yeah, because we're changing one of these negative 5 to positive 5, for instance. We're changing that from 0 to 5. So just plugging in 0 into the antiderivative usually is a lot easier of a computation than plugging in other numbers. And the idea of symmetry is really prevalent in other types of coordinate systems too. It can make your life a lot easier if you can utilize symmetry. We don't see that here. If you go on to Calc 2 and Calc 3, you'll definitely see that. So symmetry around an interval that's symmetric with respect to x equals 0, it just makes things easier to deal with. Okay. I'm going to skip this example and look at this example. I guess let me back up, and I realize it might have been a while since you've talked about even and odd functions. So how do we know an even function or if we're dealing with an odd function or neither? Does anybody remember?
It's the power of the highest term.
No, I think that's for polynomials, the leading term. Yeah, so, well, if it's an even function, you have symmetry with respect to the y-axis. So if f of negative x equals to the original function, in other words, if I replace x with negative x, and I have the same thing, then I'm dealing with an even function. Like we can think about x squared. If I replace x with negative x squared is x squared, right? So that's an even function. If you also forgot cosine is even. An odd function has symmetry with respect to the origin. You got an odd function if f of negative x is negative f of x. Or if you want to look at it, negative f of negative x is the original function. Same thing. Sine of x is an odd function. So if you're looking at some of these and it's a symmetric interval, that's usually a dead giveaway to start thinking about these two theorems, or the two pieces of that theorem. If you're still unsure as to whether the function in front of the integral is even or odd, then you've got to run one of these tests, or both tests. So really, the first thing to notice is it's a symmetric interval. I'm going from negative pi over 3 to pi over 3. And I want to break all of this up. So I want to look at these kind of individually. I want to look at it as the integral of cosine 3x minus maybe 4 times the integral of cosine times sine minus 4 times the integral of sine of x to the 5th. I forgot my dx's. So I just want to split that up, the properties of sums or integrals distribute across sums and differences. And my bounds are still from negative pi over 3 to pi over 3. So then we can look at each one of those. Is cosine of 3x, is that an even or an odd function? Cosine? Yeah, cosine is even. Think of the cosine that we wrote down of x being even. It's the cosine of w, or theta. It's even. Maybe we're not quite sure about cosine times sine, so we'll come back to that. How about sine of x to the 5th? Is that even or odd? It's odd. Well, good news, that's an odd function around a symmetric interval. All of that's just 0. Since this is even, we still have something to compute here, but we can say it's twice of the half of the area from 0 to pi over 3, cosine 3x. And I'm not sure about sine times cosine, so let's just kind of go off to the side and just test that. Is everybody all right with what we've done so far? Just identified those as even or odd functions, then applied the theorem. Let's just go down. Okay, so if f of x is cosine times sine, we're evaluating f of negative x. So that's the cosine of negative x times the sine of negative x. And since we know cosine is even, cosine of negative x is the same thing as what?
Just cosine of x.
Cosine of x, because cosine is even. Since sine is odd, the sine of negative x is what?
Negative sine of x.
Negative sine of x. So we have cosine times negative sine, which is negative cosine sine. So that's definitely not the original function. Since this is not the original, sine times cosine is not even. But notice that the opposite of f of x, negative 1 times f of x, is negative cosine times sine, which is what we're dealing with. But negative cosine sine, which is f of negative x, is equal to negative of the original function. Which means what? It means it's an odd function. Which is good news, because that makes that all of that stuff 0 too. Okay, so you might have to do that just to make sure. You don't want to assume that since I'm multiplying an odd function times an even function, that it's necessarily going to be odd. It could be neither. If it's neither even or odd, then we're kind of done there. Like, we can't compute that. So again, if you can't simplify a product or a quotient in Calc 1, then you really have nowhere to go. So all of that stuff is just equivalent to calculating this integral right here. So really, that's kind of the benefit. What is the antiderivative of the cosine of 3x? Negative sine.
X over 3.
Right, negative sine of 3x over 3. Evaluated from 0 to pi over 3.
How is that negative?
Yeah.
Oh, yeah. So is it negative? What's the derivative of sine? The derivative of sine is cosine, so we can check. Derivative of negative sine is negative cosine. We don't have negative cosine. The antiderivative of sine is negative cosine. Now notice, this isn't actually required for us to evaluate, right? I know how to take the antiderivative of cosine of 3x, and I know how to evaluate it from negative pi over 3 to pi over 3. It's just easier that we have the lower bound being 0, I think. Maybe you don't think that's easier, but it isn't 100% necessary. We see when it's odd that it's definitely helpful, but to break it up like this isn't absolutely necessary in a lot of instances. Okay, so we've got 2/3 sine of 3x from 0 to pi over 3. It's 2/3. We have the sine of 3x, so we're plugging in pi over 3 for x. What's the sine of 3 times pi over 3? The sine of pi is 0. The sine of 0 is also 0. So the net area of all of that stuff we started off with originally, there's equal parts above and below the x-axis, which is why we get 0 as our net area. I mean, even if you looked at a graph, depending on, you know, the graph itself and the visual capacity to say, yeah, it looks like the same as above and the same as below, so the net area would be 0. It's not that straightforward. But now we know for sure that it is. If you want to plot that function that we started off with, whatever the cosine 3x plus 4 cosine sine minus 4 sine x to the 5th, you could, on the interval from negative pi over 3 to pi over 3, you would see that there's as much area as above as below. Do you have any questions on this? Okay, and then the final thing here is the average value of a function. So if you can think about, hopefully we all know what an average is. The idea of averaging the function values, right, is to say, like, take all of these y values. What's the average of all of those y values? Which may seem like that's impossible to do, because to take an average, I have to take the total number, add those up, and then divide by the total number. But if I have like infinitely many y values, how does that make sense to divide through by infinitely many things? If we just start off in maybe a more basic approach and look at a function f of x from a to b, and say let's just divide that up into some subregions. I don't know. Let's do this. So five subregions. We'll call that x1, x2, x3, x4. A would be x sub 0. This would be, our B would be x sub 5. So how would we get the average of these y values? Say those are our what is that, six y values. Since we're after the average of the y values, the first thing we have to do is we have to add up those y values. So we would say that the average here is whatever a is, f of a plus f of x1 plus f of x2, f of x3, f of x4. We stop at x sub 5. Plus f of x sub 5. So that would give us the sum of all of those y values. Sorry, this is x sub 0. That's the sum of all of those y values, and then to find the average, we just divide by the total number, right? So we have 1, 2, 3, 4, 5, 6. Would that be an exact average? No, we only use 6 values. How could that be exact? Because we've got all of these other y values we neglected. All of those, all of those, all of those, all of those, all of those. So we say the average value is approximately that, but then this gives us a little bit more insight as to, like, you know, how we want to approach finding the average value of all of those y values. Is everybody okay with that kind of approach? Again, this is not something that you necessarily have to follow or remember. I'm just trying to show you where the actual theorem or the formula comes from. So if I say that, then if I take f of x sub 0 plus f of x1 all the way to f of x sub n, then I divide that by n. Well, let me start here, because that would be n plus 1. It's kind of all the same, but we're going to take a bunch of y values. Maybe this time we're taking 50, dividing by 50. But in order to make that exact, what do we have to do here? Take the limit as n approaches infinity, right? The limit as n approaches infinity would give us the exact average. Is everybody okay with that? So it's not that we're dividing by infinity, it's just that we're dividing by a larger and larger number. Okay, let's write the top in a more compact notation. So let's say that this is the limit as n approaches infinity. The top we'll just rewrite in our summation notation. That's the sum from k equals 1 to n of f of x all over n still equals the average value. And since we looked at that area, or sorry, not the area, but we looked at that function by splitting it up into a bunch of subregions, the concept of delta x, where we have the width of each one of those subregions, is still applicable here. And if we remember that delta x is b minus a over n, it's the same n, right? The n is the number of rectangles. Here, the rectangles now are corresponding to how many y values we're adding. So if we remember that, then what we get is that n is equal to b minus a over delta x. So let's put that in for our n. Invert that and multiply, and so what we have still up top, limit as n approaches infinity. We have our sum, k equal 1 to n of f of x. Inverted and multiplied that times delta x divided by b minus a is the average value. What is all of this stuff on top equivalent to? It's a definition that you should know.
Horizontal asymptote?
The limit at infinity would indicate we were finding a horizontal asymptote, yeah. So maybe my notation is messing you up. What if these were x stars? What's the limit as n goes to infinity on the sum of f of x star times delta x?
The definition of an integral.
Yeah, it's the definition of the integral. all of that stuff up there is the integral from a to b of f of x dx. And what do we do with the 1 over b minus a? Well, it's just a constant. It doesn't involve any x's. So here's your 1 over b minus a out here. So a definite integral can also give us the average value of a function. And then that's what I think I have on the next page, or below. Did I put that in there? Oh yeah, there it is. So there's your formula for the average value of an integrable function on the interval a, b. This is what we came up with. So it says, if I look at a function from 5 to 10, on average, what's the elevation that it has? What's the average elevation is another way to think about that. If that were like a mountain, from this measurement to this measurement, what's its average elevation? I guess a geometric way to look at that is to take this formula, multiply both sides by b minus a to clear this fraction. So if we have b minus a times the average value, is the integral from a to b f of x dx. And the right-hand side, we should remember that is the net area on that function from a to b. So the way we're looking at this is the net area on that function from a to b is equivalent to the average value times b minus a. Well, b minus a is just the length of this interval. So b minus a is, I guess, the width of that thing right there. And f bar is just the average y value. So it says, on average our y value is 5, let's say. So that's a value of 5, or whatever this is. So when we look at the height given by f bar and the width given by b minus a, what we're saying is that the area generated by that rectangle, b minus a times f bar, is the same thing as the net area from a to b under this function in the x-axis. So at the average value can take different flavors, because when we say value, it's just a placeholder. Like when we say instantaneous rate of change, that rate of change part is a placeholder for like whatever context. It's the instantaneous population growth, it's the instantaneous temperature change, whatever. So average value, it really just depends on what is on the y-axis. Like if we had a position on the y-axis and we say, what's the average position? We could use this formula. If the y-axis is elevation and we say what's the average elevation, this formula applies. Y-axis is temperature, what's the average temperature, and so forth. Is everyone clear on that? That value thing is just a placeholder. Do y'all have any questions on that? We'll look at an example, but we should take a break first. Everybody okay with where we're at now? Are there any questions? All right, thanks for hanging in there. Appreciate it. Okay, so there's the formula for average value on a function defined on the interval AB. Let's look at this example and find the average value of pi over 4 sine x on the interval from 0 to pi. This involves the definite integral on the interval 0 to pi, but then we also have to multiply it by 1 over b minus a. That's really the only addition we have here. So we have 1 over b minus a, is 1 over pi, then we integrate the given function. So integral from 0 to pi on the function pi over 4 times sine x dx. And the pi's will divide out. Our constant now is 1/4 times the integral from 0 to pi on sine x dx. So that's the only difference when we're looking at average value versus net area. So the antiderivative for sine is what? Negative cosine. So we have the 1/4 times the negative cosine evaluated from 0 to pi. Or we could just say that's negative 1/4 cosine x from 0 to pi. Negative 1/4. Cosine of pi gives us what?
-1.
Cosine of pi, -1, minus cosine of 0. Cosine of 0 is 1. So we have -1 times negative 1/4, or we have -2 times negative 1/4, which gives us positive 1/2. So if we say we look at that function pi over 4 sine x on the interval 0 to pi, then on average the y values are 1/2. There's our function. We're looking at all of these y values and saying, on average, what are they? So that's their average 1/2. Remember, if we look at this, let me take a picture here. If we look at that, and then say, we look down the interval from 0 to pi. So if we take this rectangle from 0 to pi, so there's our length. Length of the rectangle is pi, and the height is 1/2. Compute the area of that rectangle is the area underneath the function from 0 to pi. So I'll just draw that here. We have this area is equal to this area. So I don't know if that's helpful or awe-inspiring, but it's one way to look at it. Do you have any questions on that example? I believe the one in your homework does say the elevation is given by this function, find the average elevation, at which you would use this formula to do that. So this is, in 5.5, this is the technique, and the only other technique that we get to help evaluate definite integrals, and it is the substitution rule. So we think about the substitution rule as a reversing the chain rule. Remember, the chain rule dealt with composition of two functions or more functions, two or more. So if I'm given a problem where I have to find the antiderivative of something that resulted from a chain rule, then the substitution rule undoes that. So this allows us to find the antiderivative of a composition. Okay. So as its name entails, there is a substitution involved. So our substitution is to let u equal to g of x. And what we're looking at in this formula here on the left-hand side, this is what we're given to find the antiderivative of. And then after we substitute, this is what we're dealing with. So, just even looking at the formula, the substitution yields a simpler but equivalent function that we can then hopefully anti-differentiate. Notice what we're given. The key here, at least on the surface in the first couple of examples that we look at, is that our substitution is this function g of x, which is the interior or the inner function of capital F. The inner function here that's present, notice its derivative is also present, multiplying that composition. So when we see that, the first few examples, we'll see that it's a pretty straightforward representation of what we have here, f of g times g prime. And then we'll talk about the ways that we can manipulate that. But our substitution is based off of the inside function whose derivative is also present in the integral. So for example, to find the antiderivative of 2 times 2x plus 1, let's say to the 10th power. So the idea is, without the substitution rule, what we're stuck with doing is expanding this linear function, multiplying by itself 10 different times, combining like terms, and then integrating each term separately, that would be very tedious to do, multiply all of that out. So notice this, how it fits this format. Here's a function that's raising to the 10th power. The inner function is 2x plus 1, and the derivative of the inner function, 2x plus 1, is sitting out here multiplying that. So if we let our u be 2x plus 1, I'll just write this out one step at a time. What we're dealing with then is the antiderivative of 2 times u to the 10th dx. This is not generally where we stop. I'm just stopping here to show you that at this point, it's taking care of a portion of the integrand for us, but now we have this function of u finding the antiderivative with respect to x. That doesn't make any sense here. So not only do you have to account for a substitution, you also have to account for the differential, the dx. Okay. Is that clear? We can't take this right here and run with it. So u substitution always involves, to take care of the differential, the dx or the dt or whatever it is, we have to take the derivative of our substitution. So we're taking the derivative of u with respect to x. So the derivative of 2x plus 1 is 2. So we have du over dx is equal to 2. And then again, to account for the dx that was present in the original problem, we just take our derivative and we multiply both sides by dx. So what we really are looking at is du equals to 2 dx. So that's just always the case. When you make your substitution, you always have to take the derivative of it at some point to account for the differentials. And notice if I put du now with my u, now I have an integral of something involving u with respect to u. So that this du here being 2 dx, notice that accounts for this 2 right here and this dx right here. The other part, 2x plus 1 to the 10th, we've already saw that that's going to turn into just u to the 10th. So the original integral is now equivalent to the integral of u to the 10th with respect to u. Does everyone see that? Are there any questions at all? So what's the antiderivative of u to the 10th with respect to u? Yeah, u to the 11 over 11 plus our constant. We wanted the antiderivative of 2 times 2x plus 1 to the 10th. So then once we have the antiderivative in terms of u, then we resubstitute what u was in terms of x. So we have 2x plus 1 to the 11th all over 11 plus c. Does anyone have any questions?
So you said you accounted for the 2 up there?
Mm-hmm.
Is this 2 that we're looking at, I guess the du over dx, is that where you accounted for the 2, or is that just the derivative of the u?
It's both, actually. So when we took, since we let this be our use 2x plus 1, when we took the derivative of u, we just happened to get this 2 as well. And then really that's the whole purpose of this right here, right? Like if I don't know if this generic approach will help you, But if I let u equal to g of x, then I say that the derivative of u with respect to x is g prime. So that accounts for this right here, whatever g prime happens to be. Here, g prime is 2. But also, when we solve for du, we account for g prime of x dx. So not only do I get the derivative here, which is 2, but I also get that differential.
Okay.
So that's the whole purpose of the substitution, was to account for both the differential and the derivative of the inner function.
So it should generally always end up like that?
Yeah.
Okay.
Yeah, on the ones that are like a little bit more straightforward, yeah. So here's another example. So, up to this point, I've been saying if you've got a product, you can't take the antiderivative of it. But now that we see some of them do apply to u substitution. So what I would default to is if I saw a product of two functions of x, I would say, well, can I simplify that? Because if I can, it's going to be a lot easier. If I can't simplify it, then the only other strategy I have is to try a u substitution. That's kind of where we're always going to be. Same thing with quotients. Can I simplify it first? It's going to be much easier if I can. But if I can't, then I need to try a u substitution. Is everybody clear? Those are the only two strategies that we have, and those are the only two types of issues that we run into in this class. So what should our substitution be? What's inside the square root? What do y'all think? 3x squared plus x, is that our substitution? Yeah, not only does our substitution need to be inside, it could very well be 6x plus 1, where the outer function is to the first power, but the u that we choose, the inner function's derivative, is also sitting out there. So the derivative of 6x plus 1 is 6. That doesn't help us with the radical, but the derivative of 3x squared plus x is 6x plus 1. So that helps us with that. So our u substitution is 3x squared plus x. And really, you just want to keep track of what you've accounted for. Like, if my u is 3x squared plus x, I've accounted just for that piece. I've got the square root of u, or u to the 1/2. And then when I take the derivative of my substitution, that's when I'm going to account for the 6x plus 1 and the dx. So is it okay if we just write du is equal to 6x plus 1 times dx? Instead of du over dx and then solving for du, can we just write that? And here, I'll just write it over here, reminder, du over dx is equal to 6x plus 1. So the 6x plus 1 times the dx is just du. So we have the integral of the square root of u times du. Sometimes you might look at a substitution and think, did that actually help me? Even though the integral is simpler, sometimes you do run into the case that I can make a u substitution, but the thing that I look at as a result of the substitution isn't really any better. I wouldn't say that's common for us here, but it is possible. And can we find the antiderivative of u, the square root of u du? Yeah, it's just a power rule again. It's u to the 1/2. We have u to the 3/2 over 3/2, or times 2/3, plus c. And then you always want to resubstitute. So our antiderivative is 2/3 3x squared plus x to the 3/2 plus c. Does anyone have any questions? Before we do this next one, some of the ones on your formula sheet from 4.9, like the cosine of ax, e to the ax, those are all, I guess another way to view those is through a u substitution. Honestly, if you just remember them, it's much more efficient. But let's say, for instance, I had the integral of e to the 2x. Well, I guess we should do, yeah, because I guess we should talk about the next example, and then we can come back up to this. Or maybe we'll look at two of these, integral of cosine ax. So even with substitution, I think it's honestly just easier to remember that the antiderivative of e to the ax is e to the ax over a. Just like the antiderivative of cosine 3x is sine 3x over 3. Okay. So let's talk about this next example, and then we'll talk about the ones that are, some of the ones that are on our formula sheet. Okay, so we've got x to the 4th times x to the 5th plus 6 to the 9th. What should we attempt anyways as our substitution?
X to the 5th plus 6.
Right, x to the 5th plus 6, because x to the 5th plus 6, we see that if I let u equal to x to the 5th plus 6, I'm thinking about, well, the derivative of x to the 5th plus 6 is 5x to the 4th. But I just have an x to the 4th. So we might initially think that that's not the correct substitution because the derivative of the inner function x to the 5th plus 6 isn't sitting here. But if your derivative is off by a constant, then there's no issues with that because we can handle the constant the same way we handled the dx, just by moving it to the other side. So if u is x to the 5th plus 6, then du is 5x to the 4th times dx. But again, if I just put the du in, then I'm putting a 5x to the 4th dx back into this, while I only have an x to the 4th and a dx. So what we do with this is we say, well, it's just differing by a constant, so let me just divide both sides by 5, or multiply by 1/5. So that means 1/5 du is x to the 4th dx. Which is what's present in the integrand here. X to the 4th and the dx was what we were trying to take care of. So if your derivatives here that by your u substitution differ by a constant, that's fine. You just divide by that constant. We've now accounted for x to the 4th dx by 1/5 du. Is everyone all right with that step? So our x to the fourth dx, x to the fourth dx, that is turning into 1/5 du. And since all of this is multiplied, it doesn't really, the order doesn't matter how we put them together. So there's our x to the fourth and our dx, and then we had our x to the fifth plus 6 to the ninth. That's just going to turn into u to the ninth. So I know that's out of order, but it doesn't matter. Is everybody okay with that? Any questions? All right, so we're going to take the 1/5 out of the integral. And then we're just integrating u to the ninth with respect to u. And then multiplying it by our constant 1/5. So we have u to the 10 over 10 times the 1/5. Let's see. So that's u to the 10th over 50, and u was what? So our final result is x to the 5th plus 6 to the 10th over 50 plus c. Any questions? So can we check? What's the derivative of x to the 5th plus 6 to the 10th over 50 plus c? The derivative of our constant is 0. Derivative here, we have to use the chain rule. We have 10 times x to the 5th plus 6 to the 9th all over 50 times the derivative of what's inside, times the derivative of x to the 5th plus 6. So this is 1/5, or x to the 5th plus 6 to the 9th over 5, times the derivative of x to the 5th plus 6, which is 5x to the 4th. The 5's divide out. We just have x to the 4th times x to the 5th plus 6 to the 9th. And then we see that's the function we started with in front of the integral. So, man, I wouldn't say in practice that you check. You know, it's kind of like the derivatives. You just kind of hope you got it right. But if you have time, you can check if you want to. A lot of times they don't come out looking equivalent because then we have the algebraic simplification, factoring things out, canceling like terms. That could still be a part of why the derivative wouldn't look like the antiderivative, even if it were correct. You would still have some algebra to do. Any questions on any of this? It's like really important stuff. If you're not quite getting it, then please ask. If you're afraid to ask, then just email me. But this is pretty crucial that we understand the substitution technique. So, the manipulation of the substitution or the derivative, let's look at that in a slightly different way. Maybe it's helpful to see kind of what's involved. If we said, all right, I'm going to let my u be x to the 5th plus 6, but then I'm thinking ahead saying, well, I know the derivative isn't present because the derivative of my substitution is 5x to the 4th. So we're thinking maybe, wouldn't it be nice if there were a 5 right here? So if I put a 5 right there, if I multiply my entire function by 5, what else do I have to do to keep that equivalent? Divide by 5. So if I multiply this all so that my du is 5x to the 4th dx, that's what I'm looking at. Well, I've got an x to the 4th and a dx. Wouldn't it be nice if I had this 5 right here? So I can put that 5 there only if I multiply or divide by 5. Multiply by 1/5 or divide by 5. Right? Does everybody agree that's equivalent to the original? But now it fits u substitution kind of along the same vein of the first two examples that we looked at. So we have this 1/5 here times our integral. 5x to the 4th dx is our du. And then that was x to the 5th plus 6 to the 9th. How about that? And then our x to the 5th plus 6 to the 9th is just u to the 9th. That's where we ended up before we manipulated this and said, well, I don't have a 5 present in that original one, so I just divide. So like doing that step in the previous way is just equivalent to say, well, let me multiply by 5 and then divide by 5. I don't know if that's a helpful way to look at that or not, but that's what you're doing. So let's pretend we forgot our our table. Maybe we forgot to put it on the note card, whatever. You have to remember one or the other, the formula itself from the sheet or u substitution. So here, if I let u equal to 3x, du is 3 dx. But again, I'm looking at that function cosine 3x dx. Doesn't have a 3 involved. So let me divide both sides by 3. So 1/3 times du is dx. So then I get the integral of cosine u times du times 1/3. So my 1/3 again, 1/3 du was dx. That's dx, and then that's the cosine of u. So then what's the antiderivative of cosine with respect to u? So we'll just do this one here. Well, I have 1/3. The antiderivative of cosine with respect to u is the sine of u, right? But u is 3x. So the antiderivative of cosine 3x is 1/3 sine 3x, right? From the table. So we can look at those as a u substitution problem. I think it's easier just to know them. The one involving e, just depending on the function you're dealing with, is gonna be affect how the substituted integral looks. So here with e to the 2x, I would let u be 2x. It's the same thing. 1/2 times du is dx. So this turns into the antiderivative of e to the u, and then our 1/2 du is dx. So we can see hopefully clearly that that's going to give us 1/2 e to the 2x, or 1/a e to the ax. So anyways, the ones on your table can be viewed as a u substitution. Here's a couple of more examples, similar to what we just did. Sorry to kind of mention that. I'll skip that. All right. So why don't you give example 5 a shot? And just so you know, when you substitute, you don't want your differential like du, you don't want that raised to powers or inside the e or attached to a logarithm. Just like with the dx, you want that du by itself. It needs to be alone, not involved in any other operations. see your work.
It's fine, it's not.
That doesn't help.
It does.
It needs to be.
I just don't understand why all of a sudden you decided to include your problems that you didn't do that here. But then, and then you didn't do that here, but then you didn't do that here and over here. So I don't really get why.
So when we put the main ideas to end up with an integral, the antiderivative that involves u. But in order to take the antiderivative of a function of u, it's there. So all of these they should so this is, we said that this 2 dx, that is du.
I'm really tired.
Yeah, well, our next step should have looked something like that. Yeah, but if a kid's compete,
Yeah, but then like, what are DUs even, also what you said,
but, yeah, it's right here.
yeah, we
This-
didn't add that to our final product.
Right, because this is already, remember when it's, so like when I take the
Antiderivative of like this with respect to x,
Yeah, you see it.
that all goes away, right? It's just x cubed over 3. So when I take the antiderivative of u to the
Yeah.
thing with respect to u,
I don't know why.
that's how I get u to be 11 over 11. There is no d left over after that. Just like there's no dx left over here. It says antiderivative with respect to x. And so this
I was
just
doing the wrong
is
problem.
basically
No, I can't even.
just like this comes from this. That's just think about the du or the dx as part of this symbol. It has to have a d something. Yeah, just like when we find the derivative of x squared. Once we find the derivative of x squared, all that stuff is gone. Which one? Because in my original, I always account for x to the fourth so I just have x to the fourth in the original. So x to the fourth dx. This is too far. I forget the 1/5 du that accounted for that x to the fourth. This is dx. Those two things are just classically set place to use it. That's you. Yeah, okay, well, maybe we can talk about it. Did anyone come up with an answer here that they're willing to share?
Cosine.
Negative cosine x to the fourth over 4 plus c.
Like that?
Yeah.
Okay. Anybody else get that?
No, I didn't get a negative.
I got the same thing. All right, good. Okay, so let's see if that's right. If you check your antiderivative, if you just had cosine to the fourth over 4, if you check your derivative, you should see that it's off by a negative. So this is our u. Then means the du, this derivative of cosine of x with respect to x. Derivative of cosine is minus sine. So I mean, this is where like processes of integration can get complicated because not only we're looking for an antiderivative, but within that process we have to find a derivative. So if you're mixing those operations up, it's going to be impossible for you to do these problems. There are other techniques where you do look at derivatives and substitute as well. So it isn't an uncommon thing. But what we notice is that present in my original integral is this stuff on the right. I've accounted for that cosine cubed. To account for the sine x dx, I have a negative sine x dx. I don't have that in the original, so I move my negative with my du. So negative du is sine x dx. So the sine x dx in the original becomes negative du. The cosine cubed becomes u cubed. So we have the antiderivative of u cubed times sine x dx, which is negative du. Is everybody all right with that? So the negative 1 is a constant, so that's negative 1 times the integral of u cubed with respect to u. Power rule here, over negative 1 times our u to the 4th over 4 plus some constant. And then so we have negative 1 times cosine to the 4th over 4 plus some other constant. Or negative cosine to the 4th over 4 plus c. I don't really know. Okay, so there are any questions on that? So how about number 6? What should our substitution be? And how do we know it is a substitution? What's the inner function here?
Is it e to the x?
So we've got e to the x squared. So if I squared x first, I then have to raise it to e second, right? So the inner function there is x squared. If I think about the derivative of x squared is 2x, so just a constant difference than this other function sitting here. So again, that's always the route to know most of the time if I'm dealing with a u substitution. Derivative of this function present in the integral, then it's a u substitution. Oops, sorry. So let u equal to x squared. Take the derivative, so du is 2x dx. And again, I don't have an x and a dx left over. What I have is just the x and the dx. So I have 1/2 du is x dx. Everybody all right with that? The substitution. Then what does the integral turn into in terms of u?
So 1/2 integral of e u d.
1/2 times the integral of e to the u du. Do y'all agree? The antiderivative of e to the u is just e to the u. Then we resubstitute u was x squared. We have 1/2 e to the x squared plus c. So really the u substitution doesn't always like get rid of everything in there, right? You just have to look at the new integral via the substitution and say, is that something I know how to integrate? Is that something from the table from 4.9 in terms of u instead of in terms of x, basically? Any questions on example 6?
Would you need to bring u down into the 1/2?
Where at?
So when you get to the end, like the last part,
Yeah.
because on the other board you have it written so that it's like 1/4 e power of 4x. Would you have to worry about getting that u into the 1/2 at all?
Oh, no, because we're just kind of like seeing what we have here that's present, and we're just fitting that to what we end up with after our substitution and our derivative. So that 1/2 is just built in to this du. This over here, since our u is 4x, our du is 4dx, and we don't have a 4 present in here.
Okay.
So that's when we divide by 4. This 1/4 du, that 1/4 is this 1/4. So that one's there. Some other ones that are kind of weird, I guess, to notice at first that they are u substitutions. Something like the antiderivative of 1 over 10x minus 3. And so, I don't know, maybe you see this, that really the only viable thing to substitute would be the thing on the bottom, 10x minus 3. We wouldn't substitute for 1 or dx. So let's try this and see what it gives us. If it gives us something we know how to integrate, then that's fine. If it doesn't, then we have to sort of backtrack and think of something else. So u is 10x plus 3, du is then 10 times dx. So this right here is our u. We've accounted for that. We need to account for the 1 and the dx, or just the dx here. Our original integral does not have the 10 involved, right? There's no 10 sitting up in this integral, so we'll divide both sides by 10. 1/10 du is dx. So the original integral in terms of u is what now? Times du. Yep. So even though we're able to substitute that, then we have to look, is that something I can take the antiderivative of? Can I take the antiderivative of 1 over u with respect to u? Yeah, it's just the natural log. So this is 1/10 times the natural log of the absolute value of u. And so our final answer is 1/10 natural log, absolute value of 10x minus 3. Oh, whoops. Sorry. I went a minute over. I owe y'all a minute. So please try the homework. If you have any issues at all, let me know before class, during class, after class. It's important that we get this substitution stuff down. So next time we'll have to talk about 6.2 and then review for the final.